All right, so today we're going to go over, I'm going to go through the reading questions because there are several. We're going to talk about boundary layers. I'm going to skip lift because I wanted to go get into this other stuff because this other stuff is the stuff that I really care about. Lift is interesting, but it's not super pressing. Okay, questions. I knew if I just waited a minute, everybody else would show up. No, you're good. I ain't worried. All I have said was now I'm going to go through the reading questions. Also, I'm not going to cover lift today because I got in this morning and didn't care about lift, but I did care about sound. So, okay, so the first question is, what's a boundary layer? What does that really mean? So, yeah, let's just jump right into it because a lot of you had questions about boundary layers. So let's talk about them real quick. So when I have let's say I've got a big pipe. It doesn't really matter. Whenever I have any surface, so I'm far away from the walls of the pipe, so all I have is this surface fluid interface. The fluid can't go into the pipe because we're assuming the pipe is rigid and fixed. Okay. Now, if the pipe were soft and could flow, then you have something like the outside of a dolphin, but that's not what we have. We're talking about rigid pipes. So the normal flow has got to be 0. And right here, so if we zoom in on this really a lot, what this surface looks like is bumpy as hell. So if you got fluid, let's draw my fluid in orange. So if I have fluid particles, they're stopped by the roughness. So right at, and we're talking about sub-micron size fluctuations for some of these things. Very, very small, but that's enough so that the crosswise velocity, the parallel with the surface, is also 0 right at the surface, but only right at the surface. And we can treat it as only at the surface is the transverse velocity 0. So then it's got to go, if I'm looking at the velocity profile, here's my surface again, my velocity is 0 here, and then not 0, and then not 0, and then not 0, and then not 0, and then not 0. And then I'm in the flow of the pipe. So when I'm in the flow of the pipe, I don't really care about the wall. Now we saw from doing pipe flow last time that the boundary does in fact impact the flow in the pipe. You can see that because the radius of the pipe matters with the flow rate of the pipe. So clearly the edge of the pipe matters. But when I'm looking at just like the fluid flow, this really only cares about the shear layer, and the boundary is going to be here. This is kind of where you transition from actual flow to not moving at all. Does that make sense? So if I'm going to do something like, so if I have this sheet of paper, I can blow under it if I'm really careful, but I've got to blow under it with a really thin layer. So if I try to blow from over here, and this may work because it did work because the paper wasn't flat enough. You gotta try stuff before you do it live. So if you're trying to blow something off of a surface, and you're really and the paper is in the boundary layer, then it's not going to be able to get picked up by the flow. So if I have something that's really thin down here, this flow, the velocity is really slow here, and it can't really get under it, so it's just going to go right over it. So if you have an actual flat piece of paper or an actual flat surface and try to blow across it, it's not going to get picked up. Yeah?
Why don't the little ridges matter for like are you saying that even counting in the ridges, like there's like a little layer like this that's not moving at all?
Yeah, that's right. But so what's your?
I was just wondering, like I thought that like I didn't realize, I thought it would be like flat around that's like what I assumed before, but now I'm just like I'm just a bit confused if they're ridges, how like does it take into account the fact that it's like, you know, there's differences in height? So
well, so this, when you're looking at the ridge scale, this is like a handful of atoms high.
Yeah, okay.
So we're talking about just like a few particles of actual fluid that are really bumping into that. Fluid dynamics doesn't work for that because now you're talking about a handful of particles bashing into each other, and fluid dynamics doesn't really work for that. So you have to use like a density functional theory or some solid state tools to do this big ensemble of things, and they're actually quantum mechanical when you're looking at this scale. So from a fluid point of view, we say, I don't care about any of this stuff because it's all subgrid scale. All we do is say V is 0 right at the surface. And then as soon as you're off the surface, then it can be bigger than 0. Does that make sense? So one formula that I'm interspersing my lecture and the questions because it's relevant. Actually, I'll do the formula in a minute. Let's go through the questions first. Okay, so if you're working with a corrosive fluid in a pipe, can you coat the inside of the pipe with another fluid that is not corrosive and have your corrosive flow run down the pipe? And that's a pretty reasonable thought, I'm not gonna lie. I've been doing readings like this the entire time I've been here, and it's always valuable because people always ask interesting questions. There's always good questions that come out of it. I like this one. So I have a pipe. I'm gonna put some other fluid in it, this yellow fluid, and then run another fluid, a corrosive fluid, down the center of the pipe. So this will work, but it's going to peel off the material because you do have a little bit of turbulence at the edge. And so you don't have exactly V equals 0 in the boundary layer. So it will get peeled off depending on the viscosity of the material. So if I have a really thick, sticky liquid, then it'll stay there for a while. Yeah?
What does corrosive mean, like, physically?
Corrosive means that I've got some fluid and it's got some big, angry molecule, and it can dissolve. So I've got my peaks and valleys of my microsurface. It can start to dissolve the surface in various ways. And the dissolving doesn't ever happen in a nice smooth way. It always happens in a turbulent kind of peaky way. So you wind up drilling holes in the sides of things with the corrosive fluid. So yeah, it might work, but probably not for very long. Yeah, so that's an interesting question. Are there boundary layers between two fluids? Yes, we're going to do this next week. So next week we'll do what happens if I have two fluids and they're next to each other and moving. You have to do some perturbation theory for that, which we're going to do today. We're going to get good at perturbation theory today. What is the trace of a tensor? Oh, yeah.
A quick question. Are we going to look at water pipes where they got the hot and the cold water?
Oh, like a counterflow?
Yeah.
Probably not.
Okay.
But I can talk about it if you have detailed questions.
Not really.
This kind of just reminded me of that.
Yeah. Yeah, I had a thing that I built that had water moving in opposite direction to chill beer. I made a lot of beer when I was in grad school.
Nice.
I've since stopped because I realized I don't need to drink that much. Because when you make 5 gallons of beer, then you have 5 gallons of beer. What is the trace of a tensor? The trace of a tensor is just the sum of the diagonals. So if I have a tensor that looks like this, we'll call this Tij. The trace of T is just Tii. It's just the sum of the diagonal values. And it's a useful quantity because it doesn't change with the rotation. If you rotate the matrix, the trace doesn't change. So it's a useful indicator of what that matrix is doing.
So
Yeah.
traceless would imply that like there's no sum?
Yeah, it just sums to 0. So when we're doing this with the stress tensor, then we have dIVJ plus blah, blah, blah. Oh, sorry, actually, let's be specific. dIVJ plus dJVI, and these get an A. And then the other kinds of term that we have is the trace, which is dIVI, plus B times dIVI. Oops. So this is the trace of the tensor, and this is the tensor itself. I just make sure that these guys add up to 0 when I when I sum over I equals j, these things have to sum up to 0, so that gives us a relationship on what A and B have to be. Okay. Is this rule, do I need that? Oh, come on, draw it again. Is the stress tensor J equals mu dv I dxj? I'm just going to write it like that, even though we know we went through some symmetry arguments that say it's got to be a little bit more complicated than this because this isn't symmetric or rotationally symmetric. But whatever. It's the same thing, right? This just means that the stress or the forces are going to be proportional, linearly proportional to the shear of the velocity. And that, you can really take that as a definition of what a Newtonian fluid is. So this is so that is what Newtonian means. That means you push on it, there's a linear response in the same direction, proportional to the force. And that, so you could take that as a definition of Newtonian fluids. So we're only dealing with Newtonian fluids. Is MHD non-Newtonian? I think MHD is non-Newtonian because then the force is proportional to what the magnetic field is doing. So we'll get to some non-Newtonian fluids. But you can have other Newtonian fluids that have, for instance, a minus sign there. You can have a shear thinning liquid where you push on it and the shear goes the other direction. You push on it and it gets easier to push instead of harder. So there's other kinds of Newtonian, non-Newtonian fluids. Why, oh, I knew I was going to need it. Why, for a pipe, we had this profile. Why, and I was in a hurry and kind of sloppy with boundary conditions. I'm assuming that you guys can solve PDEs with boundary conditions. But I'm happy to actually go through that example slower and not cock up the math if you like. But one of the things that I was sloppy about was the boundary conditions. And the boundary conditions are that V equals 0 at R equals A, and dV dr at R equals 0 equals 0. And I didn't really belabor this second one because all we're doing is integrating a couple times and matching the boundary conditions and then getting the constant right. Why? The question from the reading was, why is this equal to 0? And the reason is that since it's radially symmetric, if you have a derivative at R equals 0, it has to be radially symmetric, so it has to be a singularity. So there's no way to have it, so you would have to have some kind of point and a peak, and then it becomes not differentiable. There's not a way to have it both radially symmetric or azimuthally symmetric around this way, and not have and be differentiable at the center without having a point there, because you'll always get a point, if that makes sense. So really, this is just a consequence of it's round, and we're assuming the fluid is differentiable everywhere. The upshot is that the derivative of this has to be 0 at the center. Vector notation is confusing in the book. Sometimes they're not bold. So as the comment happened, and I was like, oh, really? And I looked up, and it was like in the middle of the page that I happened to have the PDF open was the vorticity equation, d omega dt equals del cross v cross omega. And this is bold, and omega is not. I'm like, oh, yes, that's accurate. So at least it's not a math text. At least we try to make them all bold. Yeah.
For the boundary condition there, you have v equals 0 at r equals 0. Is it at r equals 0 or oh?
dVdr.
No, above.
Oh, A. Thank you. Yes, there. A. Sorry. That's my brain trying to be in advance of what I'm doing and writing the thing next now. So yeah, apologize about that. You have to keep track of when things are vectors. A lot of times when they drop the bolding, it's because you only have one component of this, and this is actually omega in the z hat direction. That's still a vector though. So Yeah, the book is maybe a little sloppy sometimes. Why in the pipe flow problem, boom. Not sure why I keep drawing this same pipe. So this is the Z direction, and this is VZ, but we throw out all the d by dz terms. So this is because the fluid flow is in the z direction, but the gradients of the fluid flow along that direction have to be 0, otherwise flow is going to pile up inside the tube, and then it's got to come out the side or something. Does that make sense? So the derivative along the flow in this case is 0. Because I have a pipe, it can't go out the sides. I know that everything I have put in has to come out at the same rate. So the derivative along the pipe is 0. This is beginning to get three-dimensional. So that's part of what makes this tricky. The boundary layer formula, which I'm going to do in a second. Did the Wright brothers understand hydro? I think so. I think all this was pretty well established, because you can see that basic lift is possible with a piece of paper. This one I know works. If you just take a piece of paper and blow over the top. Have you guys seen this trick?
I've never seen that.
Yeah, so you just blow across the top, and it's Bernoulli's principle again, or this one is maybe Venturi's. So the velocity over the top of the paper is higher than below, so the net velocity of the molecules is this way, but it's isotropic below. So you have more pressure below than above, and it pushes it up. So, so I am pretty sure they understood that. When did the Wright brothers fly for the first time? It was like
I think
1910. What's that?
I think it was
1906.
1906.
1906.
And yeah, because that crossed my mind too, and I think that the paper which described the aerofoil came out in like 1911.
Okay.
But there were people already doing stuff on like aerofoil stuff before that.
Yeah.
So I think, yeah, they probably did.
Yeah, I mean, they understood how fans worked, I think, by
Yeah.
then. I mean, they had electricity, I think, by 1906, or at least rudimentary. But Navier-Stokes worked in the mid-1800s. So Navier-Stokes equation was well established by like 1860, 1870. So they had a good 30 years of knowledge. But that's an interesting question. How was all of the knowledge in Chapter 5 established? It's all math, really. It's all this math equation that has some fascinating and interesting consequences. So Navier and Stokes and Lambert and all of those people in the 1800s were just horsing around with math and trying to come up with boundary conditions they could solve, and then go see if they did that. How does spacecraft deal with fluid flows? So that depends on what the spacecraft is doing and in what part of the atmosphere it's in. So rockets have to start on Earth. They're mostly ballistic, but they do have fins that stabilize the craft during atmospheric flight. But then the atmosphere basically falls away, and there's no more lift. There's only a little bit of drag. So the thing that spacecraft really need to worry about is drag from the atmosphere, because the atmosphere doesn't stop at the top, right? The atmosphere extends out to nominally infinity, but really it goes up for 100 miles, but then above 100 miles, it just keeps going. It's just thinner, and you'll die if you go out of the spaceship. But the spacecraft doesn't care. So there is an atmosphere that the astronauts are traveling through, and it does put drag on all of the satellites, and they do fall out of orbit because of that drag. So they have to periodically have a boost. So that's one of the things that the space shuttle did, was actually boost Hubble up in its orbit. So now Hubble's up pretty high, so I don't think we A, can't reach it anymore, and B, it's not really experiencing much drag because it's pretty high. Other spacecraft, so a friend of mine worked on this cool thing called Starshot, Breakthrough Starshot, I think. And the goal of the project was to design a way to get a spacecraft to Proxima Centauri in the lifetime of the billionaire that was funding the project. And they came up with this cool design. It's a solar sail, so okay, you need to get it to a fair fraction of the speed of light, call it 10%. Because at 10% of the speed of light, you can make it to Alpha Centauri in 20 years.
Really?
Right? Yeah.
Via solar sail.
It would be
Allegedly.
yeah, allegedly. The solar sail now, the solar sail has to be a kilometer wide.
Yeah.
Oh, okay.
And we have to light it up with a laser from the Earth that is also a kilometer wide. Kilometer wide solar sail is pretty straightforward. A kilometer wide laser is an engineering challenge. But then you've got this object that's traveling through space at a fair bit of the speed of light, and there is fluid in space, and it will, if you're not careful, poke little holes in the solar sail. So I don't know if anybody actually solved that problem, but
Yeah, but that was straight.
what's that?
Have you seen the show Three Body Problem?
Huh.
They had like a similar thing in that where they used solar sails to like send a spacecraft, and they put like atomic bombs along the
Yeah.
path, and they would explode them so that they would create the.
It was not gonna, yeah. Instead of the kilometer wide laser,
They put a bunch
they
of
put a
bombs
bunch
in
of
space.
bombs, yeah, nuclear bombs.
Edward Teller pioneered that idea in the 50s when he was really trying to make the H-bomb happen. Edward Teller wanted to use nuclear weapons for everything. He was wrong on a lot of fronts. But yeah, that idea of putting nuclear weapons behind, little nuclear devices behind the spacecraft to explode is a terrible idea. But has been cooked up before. Boundary layers and drag force, and what does Reynolds number of 1 mean? So it doesn't actually mean anything. A Reynolds number of 1 is pretty subsonic flow. It's pretty viscous flow. So there's not really a nice boundary change at a Reynolds number of 1. Yeah.
What's water's Reynolds number?
Depends on how fast it's going. So
Yeah.
the Reynolds number, remember, is a dynamical thing. Let's write it up here because we need it all the time. Reynolds number is the length of the system, whatever that is, that's the squishiest part, times the velocity of the system, which is also a little squishy, divided by the viscosity of the system, which isn't squishy, that's measurable. So it depends on the system. So you can make water have a high Reynolds number, or you can make water have a low Reynolds number, depending on how fast you're going and how big it is. Okay, the last thing that's the rest of the questions, I think. Some of you had asked about lift, and one of you asked about drag, which I'm going to get to right now. So, that's it for questions. Does anybody have any questions about the questions or other questions that I should answer right now? Yeah.
This might be a stupid question, but is there any physical meaning to like the tensor being traceless or having a trace?
Probably, but yeah, it kind of depends on the velocity, on the tensor. So for the shear tensor, pi ij is di vj. If I'm just thinking about this tensor, then the trace of this tensor is div v. So this being 0 means that the fluid is incompressible. If I write the tensor like this, so that means the fluid is incompressible. So there's probably interesting deep physics that some of my field theory high energy colleagues would be able to speak more clearly about. But yeah, yes, probably. Okay, let's talk about boundary layers. So let's talk about the drag on a sphere. And I'm going to write one solution down. So I got a sphere. I'm going to derive one of them because one is easy to derive, except for a 1/2 that I forget where it's from. There's a 1/2 that I couldn't remember how to get it when I was driving this morning. And I didn't write these notes down last time. So, okay, so if I want to know, I have a fluid with a velocity u around this sphere. And we had said before that in the absolute idealist limit, the fluid will just go like this. This is called the D'Alembert paradox, where the fluid can just move around the object. Now, if we actually, this is for an inviscid fluid, and actually, I'm pretty sure that this actually works for superfluid helium. So superfluid helium has identically zero viscosity and does all kinds of weird things. Like if I have a bucket of it, there's no intermolecular forces in here, so it will just crawl out the bucket. It'll just wick up the side and then fall out the side. Fall over. So superfluid helium does some really weird stuff. But we're not talking really about superfluids because ultimately those are quantum mechanical entangled systems, which is a little beyond what we're doing here. So there's two ways that you can write down what the drag on this, what the force is on this. So you can go through what Stokes did, and this derivation, I found the derivation, it's in Landau and Lifshitz. I found it and I was like, I only have 20 minutes to get ready for class. I'm not gonna pull it up. So I might pull it up on Thursday. If I feel like the math is worth showing you guys, then I'll do it on Thursday. But if you include the viscosity, then this force is, and this is the derivation that I'm skipping, is 6 pi times mu times rho times u squared, times u, times a, the radius of the sphere. There's some calculus stunts that you gotta pull in here, and I'm not exactly sure how to do it. But I don't really care too much about it. So the other way you can think about drag is say, okay, I've got this object. I'm gonna draw my sphere as a square right now. There's a wind moving in this direction, so think about a square truck moving down the highway. It's a little bit easier. It's the same idea. It's easier to draw and motivate. So if I have a square truck and it's moving this way at a velocity u, then in time delta t, it's going to be over here, and it has to sweep out this whole space. So this volume of fluid has to be accelerated to make way for this object. You can think about it as trailing it as well. So this is my object. It has drawn through this volume of fluid, and all this volume of fluid has to get out of the way. So the force is delta momentum over delta time. And momentum is mass times velocity, which is going to be density times volume times velocity. It's a v and a u. And the volume is the real v. The volume is going to be what's the cross section of a sphere?
Cross section?
Yeah, what's the surface area of the sphere?
4 pi r squared. That's the surface area.
That's the surface area. Just the cross-sectional area is just pi a squared. The 4 is for the whole surface area. This is just the cross-section, so just like the size of the shadow that it casts. So it's the cross-sectional area times the length, which is going to be delta t times u. Does that make sense? So then my momentum p is going to be rho times pi times a squared times u squared times delta t. Did I get everything? Rho pi a squared u squared delta t. So then the force is delta p over t is rho pi a squared u squared. The delta t's cancel out. Make sense? Times, okay, I know that this is made up. I know that it's not actually going to be like that. There's some coefficient of drag because I'm not moving through like a plug. I'm not taking a core sample. Stuff comes around the edge, right? So there's some BS factor. This is a magic factor. And there's, you read it like that, there's a reason for this 1/2. I don't remember what it is. I apologize. But it doesn't really matter because CD is a hand-wavy knob. So this is a knob I introduced because I know that this is wrong. So I introduce a knob so that I can make it right. That's how physics is done a lot of times. Yeah.
If you can write out drag as like some arbitrary function, wouldn't the 1/2 come from trying to write it out as a Taylor series?
Yeah, probably. So there's a lot of ways you can get a half. So it's either from a series or there's some geometrical thing here that's subtle that I forgot. But that's the basic idea. Yeah.
What's the difference between the forces?
Between this and this?
Yeah.
This is if I take so let's write out Navier-Stokes again. If you take Navier-Stokes and you plug it into this equation, and you plug in this boundary condition and do a little math, then this comes out. So this takes the viscosity into account. This argument is just kind of I'm just going to assume that the motion is what's doing all the work. So in this argument, we're basically throwing out the kinematic term. And with this argument, we're basically throwing out the viscous term. Does that make sense? So here, I didn't say, when I was doing this, I didn't say anything about viscosity or how the flow comes back. I'm just saying, ballpark, I've got to accelerate this, basically this much fluid. So that comes from this term. Because this is the spatial acceleration term, and this is the dissipation term. So if I match these two things together, I get CD. I can get an estimation of what the coefficient of drag should be, because in the slow limit, this should work, and I should get this answer. And in the fast limit, this should work, and I should get this answer. And they basically should be the same system, right? So I can just set these two forces equal to each other and get an estimate of what the drag coefficient is. And there you get 12. The pi's cancel. I get we're going over to this side of the equation, so I get a sorry. This is a mu, not a nu. So there's no rho in this equation. I wrote that down wrong. I can rewrite this as nu times rho, which I'm actually going to do. The book uses mu, but mu and nu are related by rho. So here I'm left with 12 times nu over a times u when I do all the math. And this is just 12 over the Reynolds number. So what this says is the drag coefficient should go like 1 over the Reynolds number. So that's intriguing. So the faster it goes, the drag coefficient should go down a little bit. But drag still goes like velocity squared. So the drag is going up, but the drag coefficient is going down. So what does it actually look like if you plot it? So if I look at the drag coefficient versus the Reynolds number, it does in fact go down like we predicted until you get to a certain Reynolds number of like 20 or 30 or a few hundred, and then it flattens out, and then it does something weird. Who even knows? Then it gets, because then the flow gets turbulent, and the turbulence isn't anywhere in any of this argument. So, and it's more complicated. And the result is because of the boundary layer of the flow going around the surface. It's going to do something complicated. Yeah.
What are the variables? What is the drag coefficient equal to?
Here?
Yeah.
This is 12 times nu, the viscosity, over the radius times the velocity. And nu, a, and u just give me my Reynolds number, which is over there. So this is just some number over the Reynolds number.
Could you go over how you got the drag coefficient again?
The which?
Like how you got the 12 nu over AU.
This? Yeah, so I've got these two arguments for what the force on this sphere should be. One comes from considering this term primarily, and that's this equation. And the other one comes from primarily considering this term, and that's this bulky thing that I did. So I set these two things equal to each other, and then I just solve for CD. And a lot of stuff cancels, and I'm just left with that. So that's just algebra. Okay, so that's all I have to say mostly about that. So the book also then goes into the shedding of von Karman streets, which is intriguing. So what does this boundary look like? Let's talk about a little bit more idealized case of what the boundary should do. So if I just have I'm sorry, I should have said this at the beginning. There's a reading that went up this morning that's due tomorrow. Imagine you guys all get alerts from Canvas, right? It's not super long. It's only 2 sections out of chapter 6, so it should be shorter. So I apologize about A, not giving you much time, and B, giving it to you the same day that there's a homework due, but it's not super long. And I'm going to spend a lot of time with that reading, and you're more than welcome to just kind of half-ass turning something in and then read it again later. That's fine. So if I have a surface, this could be the inside of a pipe, or it could be the side of my sphere, as long as I zoom in close enough so that this part looks flat. That's another physicist stunt. I have d by dt of v plus v dot grad v equals -1 over rho grad p plus nu del squared v. So if we just start thinking about blowing across a surface, like you've got a wind across a surface, you've got a leaf blower that's dumping air onto a surface, you have some initial start, but we know that v normal is equal to 0 and v tangential is equal to 0 right here. Now we're going to look at this equation. Let's expand it out again. So we're going to assume that we're in steady flow. And steady flow means the partial time derivative of velocity goes away. It's not static. There is still a velocity. It is still going to accelerate in space, but not in time. So I just have a leaf blower that's parked here. I've got some big velocity here, and you know that if I stand far enough away from a leaf blower, you can't feel it anymore. So there's some derivative of the longitudinal velocity, even though I could stand there for a long time and feel the same leaf blower blowing on my face. So this term would go away. This term will expand out. So this is Vx d by dx Vx. Let's only consider the x component of velocity. So we're expanding out this. So remember, this is the acceleration in space. Is Vx d by dx and Vx. So this part's the operator, and this is the thing that we're operating on. Plus Vy d by dxy, that's the second part of this operator, times Vx again, equals, well, let's just assume that the pressure gradients are 0, and I'm just blowing fluid into a region, is going to equal nu times d squared by dx squared of Vx plus d squared y Vx. Okay. Does everybody understand everything in this? If not, I would say it again slower. So we've thrown out this term, we've thrown out this term, expanded what this one is, and expanded what this one is. So now let's throw out more terms. Doing physics is just throwing out things you don't feel like dealing with. We're going to do this again hard when we do linearization in a minute. So what of these terms can I throw out? So Vx is significant, right? That's the primary quantity that I'm after. And I know that it's going to decelerate as I move along this direction. So Vx d by dx, this probably is a term that I need to consider. But Vy, that's small. And gradients in y are probably also small. So let's throw this term out. And then let's think about the viscosity term. Really, the viscosity term is the shear term. So the term that we really need to consider is the y part here. And we can throw this part out because the viscosity is not really acting along the flow. It's acting transverse to the flow. So after judiciously throwing things out, we're left with Vx d by dx of Vx equals nu d squared Vx d by dy squared. It's gotten so much simpler. Does this make sense, how I got here? So I started with Navier-Stokes, threw out stuff because steady, threw out stuff because geometry, threw out stuff because that's about what it's going to do in the equation. So now we're just going to ballpark this. So this is 2 Vx's, that's V squared, and this is an L. So the velocity in the x direction changes over some length scale L that's along the flow. And the boundary condition is going to have some thickness, which we'll call delta. So my first term is going to be v squared over my long length. And this term is going to be nu times v over delta squared. So here I turned derivatives into fractions because I'm a physicist and I can do that because I can just wave hands, right? So this is velocity over some kind of length. We're just going to say my length is this long length. So then we just solve for the thickness of the boundary condition layer, and you get that delta equals a v gets canceled, a nu gets canceled, a nu goes down over here, and you're left with L nu over v, square root of that. So the boundary layer gets thinner as the velocity gets higher, and thicker as you move downstream. So this is, if you've ever watched a pool jet, you can see they have this flare, and then they mix, and then all of my hand waving goes away because it mixes very quickly and becomes turbulent, and all of this stuff goes away. But you can see as the jet enters the pool, it flares out. And this is very useful. So it tells you that the further away from the source you are, the boundary layer is thicker. The higher the velocity, the boundary layer is thinner. So this is all useful. Yeah?
Would it be possible to run through the parts that you drew out and the y you drew out one more time?
Yeah, totally. Right, so we start with Navier-Stokes. We have partial v partial t plus v dot grad v. So this is the time acceleration of the velocity fixed in space. This is the space acceleration of the velocity fixed in time. Pressure gradient and dissipation. So we just expand out, so we're assuming that we're in steady flow. I just turn the leaf blower on and I hold it there. And I'm just staying there. I'm not doing anything subtle. So this goes away. We're going to throw out pressure gradients because once the air leaves the leaf blower, there's no pressure gradients anymore. It's already moving. So we throw out that term. And then we just expand out what the other things are. So we're left with vx dx on vx. We have vy dy on vx. That's what this term means. And then we have the del squared v. We have nu dx squared vx dy squared vx. So vx is big, vx is big. We know that it's going to change along the flow. So we have to keep this term. Vy is 0 right here. It doesn't come out with any transverse velocity. So we're going to throw that term out. And also gradients in I should say y. Gradients in y and vx are not huge, but mostly the vy term is really small. So this term goes away. We're not pushing velocity up this way with velocity. That's what this term says. And then for the dissipation terms, the dissipation really happens in the transverse direction to the flow. So you really need to consider the cross derivative because that's where the dissipation is happening. So we throw out the dx squared term and we just are left with the dy squared term. And then all we're left with is vx d by dx times vx, acting on vx, that's not times. And then nu times d squared by dy squared of vx. So we're balancing these two terms. So this is the deceleration because it's running into the crap versus the deceleration because it's getting sheared apart. And then we're left with this useful formula. And this useful formula will show up again because I like it. Okay, any other questions? How am I on time? All right. Way worse than I expected. Was that?
That clock is working on it.
Yeah, they fixed it. That's definitely the right time.
No way.
I know, right?
That's right, I can't actually see it, so. Okay, now I have a half hour left. Right here. Okay, so boundary layers are fun and cool and a lot of hand waving. So that's one thing about this class is we wave our hands a lot because we can't actually solve the things that we want to solve. Let us okay, I will do thermodynamics. So there's some thermodynamics in the text. that you'll read tonight, tomorrow night. It's not very long, and the most important thing he goes through is the expression when in an adiabatic fluid, P equals rho to the gamma with some constant in front. I'm going to derive this, but I'll do that after I do linearization, because we're on a throwing things out kind of kick. So I'll come back to thermal, even though we need it for doing sound. We're going to talk about, yeah. So let us say, just in general, that I have some system that says f of q equals q dot. Now here, dot, there's no partial derivatives in anything that I'm going to say for the next couple of minutes. Dot is dq dt, where q could be spatial position or really whatever. Or you could have a more elaborate function, like this could be some function of the derivatives, but we're going to stick with this general but not completely general argument. So this is my equation. I don't know, I may not know what f is. I may not know what f is. So let's say I know what f is and it's horrible. It's like the sine of the tangent of the exponential of the thing minus 7 to the 5th plus 6, right? Some horrible function that you know you can't differentiate, or you know you can't infer, some transcendental function. But I do know that, or really, okay, so I should be explicit. This is q dot evaluated at q naught. For some value, I have a solution. Does that make sense? So however I do it, and typically it's, I set this equal to 0, and I solve for when q makes the derivative 0, and then I have my fixed point. So sometimes it's I solve for equilibrium. Sometimes it's there's an obvious answer and I can just write it down. A lot of times none of that's true and you just have to make something up or measure something. So I know something like this. What I want is the answer for some q1 that is close to q naught. What I want to be able to say, so I can say that, let's say we want the answer for q naught plus q1. q1 is small. Now, when you're doing perturbation theory, a lot of times people will insert an epsilon here and keep track of epsilons and count how many epsilons. Have you guys seen that happen before? Yeah. That really only happens, sometimes that's how people do it. A lot of times they just say, this guy's small, he's an epsilon. Q naught doesn't have to be small, that's an actual number, but Q1 is some close deviation. So then I can write down f of Q naught plus Q1 equals Q naught dot plus Q1 dot. This is fine. Whatever f is, I can say this because this is true, right? So I can just ask what f is doing at these 2 points. Now what I want to say, and here is that's a factory. So there's some machinery that I'm going to talk about in a second. And after I'm done with that machinery, then I can say f of Q naught plus f of Q1 equals Q naught dot plus Q1 dot. And then, because I know this is true, I can cancel out these guys, and I have the solution to my equation, which says that Q1, f of Q1 is equal to Q1 dot. And I already know how to solve it for 1, right? Does that make sense? So basically, I know some solution And I want to know what solutions are that are close to that solution, so I'm going to do a Taylor series. But that's the Taylor series is in here. So I'm just skipping a step and saying what I want to get to. So you usually can't say that f of q naught plus q1 equals f of q naught plus f of q1. This is special. This is only true if f is linear. If f is a linear function, then I can do this splitting apart. And then if I have one solution, I can get another solution. But if I have something horrible like a square in there, then this isn't true anymore. And I have to figure out a way around it. And the way we get around it is with Taylor series. So I make a Taylor series of f. So I say f of q naught plus q1 is equal to f at q naught plus q1 times df dq evaluated at q naught, and then I'm done. Let me write that up bigger. That's the smelly jelly, as it were. That is the funky sauce. F of q naught plus q1 by Taylor equals f of q naught plus q1 df dq evaluated at q naught. Does that make sense? So that's basically all we're going to do. Because then what can I do? Then I have q1 times, I'm going to call this smiley face. I'm going to call this bit here smiley face. So that we don't get bogged down in details. Because this is just a number. df dq evaluated at q naught is just a number. So this term is q1 times smiley face. So q1 times smiley face equals q1 dot, because this is now true. And now I can solve this. I didn't tell you what the hell q1 or f or any of this crap is. Q could be the number of underpants in my dirty camper. Like, it could be whatever. But I linearize it, and now I have something that I can solve, and now I know that q1 equals q naught e to the smiley face t. Everybody follow that part? So this is just something, it's a thing equal to its derivative, that should be equals. I can just solve that, and then I'm left with an exponential. Does that make sense? So that is the crux of how linearization works. And this is how it works in all of the times that you're going to run into it in math, but it's not always going to be quite so elegantly spelled out. And when you read it in the textbook, all they say is, they write down Navier-Stokes, they tell you what their equilibrium solution is, and then they say, we did that. And then they have a dispersion relation, which is omegas and k's. And you're like, how did you get omegas and k's? There's no omega or k. Well, let's talk about omega and k too. So we'll come back to this, but the basic idea is, let me write it over here. F of q equals q dot. F of q naught equals q naught dot. So these are the givens. F of q1, q naught plus q1 equals q naught dot plus q1 dot. That's all just true, because I'm just plugging stuff into machines. Do a Taylor series on this guy, and you're f of q naught plus q1 f prime of q naught equals q naught dot plus q1 dot. And then we can cancel out the solution that we know, and we're left with a differential equation that we can probably solve. We're left with a differential equation that we know we can solve. I know I can solve that. It's linear. It's a linear differential equation. And I know that solution. I know that solution. So the thing is, whenever you're linearizing things, you're going to get stuff that looks like this. Or something that oscillates. What's the difference between this and something that oscillates?
It should be imaginary.
Where do I put the imaginary?
E to the I.
Yeah. Sometimes this comes out to be imaginary. And because e to the I theta equals sine, cosine theta, don't write that wrong, plus I sine theta. There's some things that I'm probably never going to write wrong, and that's one of them. There's a lot of things I'm going to write wrong because I'm an idiot. But that one is so grained into my head. My sister's a mathematician, and she has that tattooed on her back. She actually has e to the I pi plus 1 equals 0.
On her back?
Yeah. But I'm just on her shoulder. Not like huge on her back. It's
Right,
tasteful.
okay.
It's nice. It's like, oh, that's cute. It's not like a huge gang sign. This is one of the most beautiful things that you can possibly write down because it involves all the special numbers. E and I and pi and 1 and 0. Those are all the really important special numbers in math. So, okay, so was that?
I have a friend that tattooed a ladder of like stepping up and down with raising and lowering operators.
That's awesome.
Yeah.
That's fun. I mean, that's particle creation. That's awesome. That's why we're here. Okay. So this is how linearization basically works in the most abstract case. And we're going to get to this in a second. But basically, we're going to introduce a bunch of little things and then throw stuff out. So one of the things that we do is, there's a step in here that I missed. So in here is throw out all, come back, chalk. Oh, I gotta change the color. The Q1 squared terms. So we make this linear by throwing out everything that isn't linear. Largely arbitrarily. But if Q1 is 10 to the minus 3, what's Q1 squared? That's 1 over a million. That is a small number. Okay, so that is the bulk of linearization. So now I'm going to use all of this in a second, and will I do it today? I might not get to it today, because I need to talk about Fourier series. So, given all of this, now, and given this, this is maybe the most important equation that anybody's written down, is this one right here. Because it allows Fourier transforms to happen. And our understanding of Fourier transforms enables quantum mechanics. It enables communications. It enables so many things that are crucial for modern life come from the Fourier transform. So let's talk about Fourier transform for a second. So I have some function f of x. And you guys, hands up if I have seen Fourier transforms somewhere. I love Fourier transforms and I'm super comfortable with doing all kinds of weird crap with them. Maybe.
I only love them. I don't
Yeah,
love them.
nobody loves them.
You will. They're so
Oh,
great.
no.
So good. The Fourier transform is so good because it takes this and turns it into that.
That's very
Because this is a sine wave. It's complicated, but I know the frequency of this sine wave. It's just a number. It's just that, right? So it enables vast simplifications in a lot of scenarios. It enables, if it weren't for the Fourier transform, we would not have autotune. How important is autotune? So how does autotune work? Autotune works by cutting up the sound into little tiny bits, doing a Fourier transform so that it's in frequency space, moving it to the right frequency, and then doing a Fourier transform back, all very fast. It's super elegant and simple. Like it's a beautiful thing. And then bad singers can sing in tune. So for us, what can we say? So I have f of x, and it is some series of sines and cosines. We're going to write this as f hat of k e to the I k x dk. Okay, you always have to remember where the k is. What are you integrating over? What are you changing into what? So, so if I take f of, oh, and the inverse transform, I can undo this. F hat of k equals the integral of f of x e to the minus I k x dx. Everybody good with that? Has anybody not seen it written this way before? So I can spend a minute with it. Okay, good. So this is very cool. One of the most important things that we're going to do is, so I've got a couple homework problems on Fourier transforms, just like take the Fourier transform of Gaussian and get another Gaussian, take the Fourier transform of a sine wave and get a delta function. Just so you put your hands on these basic functions. So it's lots of fun things to skip in here. One thing that I'm going to show you is what happens if I take a derivative. If I take a derivative, d by dx of f of x, this is the integral of f of k, d by dx of f of k e to the I k x dk. This doesn't depend on x. This doesn't depend on x. The only thing that depends on x is that. And I know what that is. D by dx of e to the I k x equals what? I k e to the I k x. So this is just I k times f of x. Well, that kind of blows f of k e to the I k x dk. But the important thing is that derivatives in space turn into multiplying by I times k. That is where at least half of the power of Fourier transforms comes out. Because I can do something in Fourier space. So derivatives are a headache, but multiplying is easy. So if I want to solve something, if I have a differential equation I want to solve, I can do the Fourier transform of the whole thing, just multiply by k, and do the transform back, and you have a solution. So this is how we solve gravity. So I have this code called ENSO that we use to make big galaxies and cosmology simulations. And we solve Poisson's equation. Poisson's equation says del squared phi equals 4 pi g rho. Have you guys seen this for gravity? I have never seen that before. I've seen that, but it's a little dodgy. Okay, so we'll come back to where this comes from. This is equivalent to, it's equivalent to f equals g m m over r squared minus. So it's equivalent. You got to do a little bit of calculus, and I'll actually do that so that you've seen it, because it doesn't show up a lot. But when I solve this in the code, I take a Fourier transform of both sides, so that I'm left with del squared phi hat equals 4 pi g rho hat, and now I'm in Fourier space, but this del squared just becomes a minus k squared. So I just divide by k squared over here, and I have a potential. So I boost to Fourier space, and that's easy. It's a function in the computer, and they do it really fast. So I do a Fourier transform, divide by k squared, and then transform back, and I have the solution. I don't have to worry about actually solving this differential equation very much. I just have to apply the Fourier transform. So that's what we're going to do with sound waves on Thursday. Yeah. I got 8 minutes left. So when we get to differential equations like this, you can solve this with a Fourier transform super easily. It just pulls down an IK omega, which we'll talk about. We'll do that again later. Let me do the thermo really quick, because I want to, because it's not super long and I want you guys to see it, but maybe I'll do it again on Thursday if this is too quick. Okay, so we talked about Fourier transforms. We're going to come back to all of these things on Thursday when I do sound waves. Okay, so the first law of thermodynamics, and this is, I recognize, not really doing justice to the topic because I'm going to race through this. But stop me if you know anything. If I don't get to the end, I'll pick it up later. So the first law of thermodynamics says that heat flow equals energy change plus work done. Okay? So this is the first law of thermodynamics. It's just conservation of energy. Energy comes out, either you have to have done work on the thing or you have changed the internal energy of the system. So we write this down in a differential sense as saying dq, which is a tiny little bit of heat flow, differential, infinitely small. As small as you need it to be, smaller than that. Not so small that it's not valid anymore, but small. dq equals dE plus P dV. And this has come up already once in class. So this is a tiny little bit in heat, a tiny little bit of energy change, and a tiny little bit of work. So they noticed that there's this other quantity called entropy, and if you say ds equals dq over t, this is just found by screwing around with math. So they were just horsing around and they saw that this is another variable that is useful for defining the state of the system. So this is a state variable.
Sorry, E over here is temperature, right?
Yeah, T is temperature. So a state variable is anything that has to do with the way the fluid is, not what it's doing. So state variables are like the pressure, the density, the volume, the temperature, and now the entropy. But Q, heat flux, is not a state variable. That's not a thing that it has, it's a thing that it does. So Q is not a good state variable, but S is. S is just dq over t. And they noticed this by just doing math with these things, by being, 1830, and they didn't have the internet yet, so they couldn't waste all their time watching YouTube videos of kids playing Minecraft, or whatever you waste your time doing. So this was described experimentally, and the only thing that they knew was that it was a good state variable. They didn't really know what it meant, and it took a while. So one of the things that they learned was that it always has to go up, but that's all they knew. It took until Boltzmann to really get a good understanding of what entropy is, but that's for a different class. So entropy is just a state variable that goes up. So we can say that ds equals dE plus P dV. Okay, so now I'm going to write down a couple other things, and this is going to feel like I'm kind of pulling things out of the air, because right now I am. Yeah.
Wouldn't that be tedious?
TDS, thank you. TDS. That's what I get for talking and writing at the same time. So this is one of the famous TDS equations. So there are several TDS equations. You can throw in enthalpy and other things and get different things on the right-hand side. But these equations really dictate thermodynamics, and when you get to proper thermo, you will learn to love these TDS equations. When you get to thermo the second or third time you see it, you will love the TDS equations. The first time, they're a little opaque. So what do we know? So we know that dE equals CV dt. So the internal, what this says is that the internal energy only depends on the temperature. And by this quantity CV, which is the specific heat at constant volume. So if I take a bottle, I seal the end, I put some heat in, I see how much the temperature goes up, but it's a sealed volume. The volume's fixed. We also know that P equals, that's right, PV equals nRT, or R is the Rydberg constant. The Rydberg constant? No, which R is that?
R, I mean,
It's just R.
gas.
Isn't
It's the
that?
gas constant. There's not a name associated with that. Was that?
Yeah, I was just thinking.
It's just the gas constant. Rydberg is 13.6 electron volts, right? We also know that, okay, we can do a little bit of work and we see that CV equals R over gamma minus 1, where gamma is equal to CV over CP, the ratio of specific heats. You don't really need to know that that's what it is. Gamma is the squishiness of the gas. It tells you how many extra degrees of freedom you have to dump material, to dump energy into. And for an ideal gas, this is 5/3. For a monatomic gas. Oh, and now I'm out of time. I'm just going to start here. I'm going to stop talking and pick up here. So we've laid out the stunt. What we're going to do is we're going to take these and cram them in here, do a little bit of calculus, and what we're left with is P rho to P equals a constant rho to the gamma. That's what comes out of this. It's a little bit of algebra and some logs. It's nothing really super complicated. But I'll do it next time because I'm out of time now. Okay, does anybody have any questions about the stuff we went over today? Yeah.
Is gamma is equal to CV over what?
CV over CP.
What is that?
Squishiness.
CP is squishiness?
No, CP is the specific heat at constant pressure, and CV is the specific heat at constant volume. You now no longer need to remember that because I'm not going to use those quantities except in the gamma. Okay, any other questions? I'm going to stop the report. Yeah.
You said it was 5/3 for.
For an ideal monatomic gas, so if there's just one atom in the molecule, if there's a diatomic gas, then it becomes 7/5.